This conference will now be recorded.
So the presentation, we'll be able to stop a couple times during the presentation to ask any questions. You're also welcome to use the chat feature over on the right, and you can send any questions that you have over through that. With that, I'll turn it over to Andrew Dawson, who is going to be our presenter today.
Well, good afternoon, everybody. Thank you for making it today. Name of my presentation is GaGe digitizers in ultrasonic applications. I'm unmuted. There we go. Okay, sorry. So my presentation is divided into three parts. First, I give an overview, an introduction to ultrasonics, and then I'm going to focus on a specific ultrasonic example in which I was involved way back in the 90s, actually back in the last century, last millennium even, back when I was a teenage researcher. And then finally, we'll move on to discuss some digitizer features available on our GaGe CompuScope digitizers that are specifically useful for ultrasonics. So we start with an introduction to ultrasonics. Ultrasound, the theory of sound generally, is encapsulated in this book by Lord Rayleigh from the late 19th century. This is one of the few science books from the 19th century that's still in general use. And I think it's sort of safe to say that this is really the last word on the theory of sound. Sort of modeling it as balls and springs really works. There's been a lot of progress since the late 19th century in other domains, but sort of sound has kind of been solved since the late 19th century. That being said, sound in solids is actually quite complex. You have a number of different sound propagation modes, which we show here with the slinky on the right. So on the top, we can see a longitudinal wave, compressional wave, where the motion of the particles is along the direction of propagation. And we got a transverse wave below where the motion is perpendicular to the direction of motion. And indeed, the speeds can be slightly different between the compressional and the transverse. And you can even have two transverse modes, up, down, and left, right. Those can have different speeds, slightly different speeds. And you get complications such as mode conversions, where if you send in sound at a certain angle, you can get it changing from longitudinal to transverse to back again. You get this case where if you try and reflect a sonic beam off of a solid, you can actually get three reflections, a longitudinal and then two transverse. So we won't address any of those complications. We'll talk strictly about longitudinal waves propagating perpendicularly to interfaces and so forth. But I just want to point out that while solved and completely understood, sound in solids can be quite complex. Sound is quite a powerful tool for probing solids generally. I mean, we call it non-destructive testing. People have been hitting objects they produced with a hammer and listening to the sound to determine the quality for millennia. Specifically here, we're going to talk about ultrasound or ultrasonics. Ultrasound being defined as sound with a frequency beyond the range of human hearing, which is above about 20 kilohertz. I'm going to sort of propose a possible alternate definition of ultrasound later. The key point about sound is it's generally non-destructive if you use it at low intensity. We'll talk about non-destructive testing and non-destructive evaluation of industrial materials. Another domain that we work with a lot in GaGe is medical ultrasonics, and often there you're actually doing destructive or maybe non-destructive ultrasonics, where you actually can use high amplitude ultrasonics to do things like boil away tumors, which we'll have a brief look at later. Moving along, talk about some different types of waves in solids. We really want to focus on waves that'll tell us about intrinsic properties of the solid rather than things about its dimensions. Here we've shown as L, its length. So first we can talk about surface waves, like waves on the surface of the sea. Thing is, those often depend on the depth of the body of water. In fact, this is why the waves break in that curly fashion they do against the beach, because the depth is changing as the wave is coming in, so it executes that bizarre motion. But as I say, the key thing is it depends on the depth. We're looking for something that depends only on the material properties. If we take a bulk wave, not a surface wave, with low frequency, a low wavelength lambda, such that the wavelength is greater than, big wavelength, long wavelengths, bigger than the size of the sample, or at least it's similar to the size of the sample, then we tend to get like resonant phenomena. This would be like plucking a guitar string. You don't really get well isolated waves, and indeed the phenomena changes quite markedly if you change the length of the guitar string. So it's very sensitive to the dimensions of the thing. If the guitar string were 20 miles long, then the wave when you pluck the string, the wave propagating would look more like the bulk wave below, where we've got wavelengths. We're talking about wavelengths that are much smaller than the size of the sample, and then the wave propagates more as a isolated packet and bounces off of interfaces and so forth. We can almost say it starts to behave more particle-like. It travels with a well-defined velocity, as opposed to executing a resonant behavior that is sort of collective and associated with the shape of the sample. If we look at the famous wave equation here, let me get my laser pointer, control, yeah. If this is the wave equation that applies to all waves, and in fact kind of applies by definition, that the speed of propagation is equal to the frequency times the wavelength. And if we plug in a typical sample size of 5 millimeters and the speed of sound roughly in steel of 5 kilometers per second, we wind up with a frequency of around a megahertz. So that means with a 5 millimeter thick piece of steel, if you get beyond a megahertz of frequency, you can propagate these packet-like pulses of ultrasound through the material, and then look at echoes, which are very easy to interpret, as we'll see. Okay, so that kind of gives us, as I say, an alternate definition of ultrasound, which is such that the frequency is high enough that the corresponding wavelength is less or even much less than the size of the sample. This is the most theoretical slide of the presentation, where we look at the speed of sound. So the speed of sound, quite simply speaking, can be calculated as the square root of the stiffness of the sample divided by its density. And it's no coincidence that this looks very much like the formula for the resonant frequency of a spring mass oscillator, which is the square root of the spring stiffness divided by not the density, but the mass of the bob on the end of the spring. A second important quantity that we talk about in ultrasonics or acoustics is the acoustic impedance, which is nothing but the product of the density and the speed of sound. And from this acoustic impedance, we can calculate the reflected intensity, which one would receive if one bounced sound off of an interface consisting of two materials with impedances Z1 and Z2. This is also equal to the square of the reflectance. So you can see right away, if the two materials are the same and the Z or the Z, the impedance of both is the same, then of course the reflected intensity is 0. So we know that sound reflects off interfaces. If there's no interface, there's no reflection. The bigger the mismatch in impedance between the two materials, the greater is the reflected intensity. Okay, so this is a key point in ultrasonic inspection. Right away, it explains why you don't hear your neighbors fighting in the next apartment. It's not because the sound gets attenuated in the walls separating you from your neighbors. It's because most of the sound from their yelling, because of the huge acoustic mismatch in acoustic impedances between the air in their apartment and the solid wall, most of the sound of their yelling bounces off the wall, and then it gets absorbed by the couch, and then bounces again, gets absorbed by the carpet, and you only hear, mercifully, a trickle of the sound coming into your apartment. If we look at this table below, I've compiled for a bunch of typical materials of growing density, we can see that although the density increases of these materials from air all the way to stainless steel, the speed of sound also increases. If you look at the top equation there, you might expect the speed of sound would go down as the density increases because the density is in the denominator. However, the fact is that the stiffness increases so much faster than the density that it overwhelms this reduction factor caused by the density, such that the velocity as you make something more dense actually goes up because its stiffness tends to go up so quickly. So as we can see, the speed of sound increases from a low of 0.33 kilometers per second way up to 7.9 kilometers per second. An interesting note that 0.33 kilometers per second, that's pretty close to 1 foot per millisecond, which is about exactly 1/1,000,000th of the speed of light, which is a foot per nanosecond. So sound in air travels about 1,000,000 times faster than light in air or vacuum. And this sort of explains why people who do ultrasonic inspection and people who do radar look at similar signals, but the size of the objects is about 1,000,000 times different. The ultrasonic inspector looks at millimeter size objects, whereas the radar person looks at things that tend to be a kilometer away, and maybe not a kilometer size, but distances of a kilometer away because of that factor of million between the two propagation speeds. If we look at the acoustic impedances there, we get that column, but then we can calculate the reflected intensity of sound in an interface consisting of water and the material. So of course, if we have a water-water interface, we get 0% reflection. If we bounce sound, if we're in air and we bounce sound even off something as relatively unstiff as water, we get 99.9% of the reflection bouncing off. So this is why you can't hear people very well when you're underwater. It also means that key thing is that if the sound gets reflected off, then it doesn't go into the material to probe it. So if you're trying to probe the water by yelling at it, that wouldn't be very effective because only 0.1% of your sound energy would actually go into the water to probe it. We can look at the different values here. Typically, we're looking at often in industrial materials at steel type materials. So we can see that with sound going through water and bouncing off steel, about 90% of the sound energy is coming back at us. That only means only about 10% is going into the steel, but that's still a fair bit. As we can see, if we tried to inspect the steel slab from air, we would have had all but 0.004% of the sound energy coming back at it. So only 4 milli% of the sound would go into the steel slab to probe it. So that explains why a lot of the time, most of the time even, when we probe things in ultrasonics, we do it with a sample immersed in water in order to get that good impedance matching. So often ultrasonic scanning systems are in what look like big fish aquariums. A word about how we produce ultrasound. One of the most popular technique is to use a piezoelectric contact transducer. That's a material like quartz, where if we apply a high voltage on it, it moves. And in fact, if we apply a very short pulse, maybe a microsecond wide with an amplitude of 300 volts, we'll get sound, we'll get motion produced by the it'll sort of breathe at a well-defined resonant frequency that's related to the round trip time through that crystal wafer of quartz. That's what I'm saying. But this is what we call a narrowband transducer. It rings for a long time, so you get this very long sine wave, which is not going to be appropriate for ultrasonic inspection. We're going to want very short pulses so that we can see separated echoes. And the way they do that when they produce a conventional contact transducers, just put a blob of dampening epoxy on the top of the transducer. So now it doesn't ring for a long time, and you get this nice short tone burst, we call it, with a well-defined central frequency, but a duration that only lasts a few cycles. Once we've got our contact transducer, we represent it by this little box with an X in it, and you could put that right on your sample. There's two problems with that. One, in order to scan the sample, you're going to have to scrub it back and forth, which is going to require application of some sort of grease to facilitate acoustic contact between the transducer and the sample. But second of all, you're going to be generating, where's my laser pointer here? You're going to be generating the sound, but then the sound that's being generated is going to get mixed up with the sound that's going to be reflected back. So in order to solve this second problem, what we often do is separate the sample from the transducer using a buffer rod. We choose the acoustic impedance appropriately to get the right amplitude of echoes coming off. And now our emitted echoes don't sort of get mixed up in time, don't occur at the same time as our reflected echoes, and we can separate them better. But it doesn't solve the first problem, the scrubbing problem. That's solved, as I say, using immersion transducers. So we put our sample inside inside of water, and then we can scan our probing transducer back and forth without having to worry about scraping it across the sample. Okay. How do we actually do the ultrasonic inspection? Well, first of all, we divide ultrasonic inspection in two. First of all, we have non-destructive testing, okay? So typically we, as I say, send sound through the water. It bounces off the sample. We've got a nice flat sample here, and we get a front wall echo from the front wall of the sample, and that's shown here in the signal that we acquire with our digitizer. And then some of the sound travels into the sample, bounces off the back wall of the sample, travels back and out again, and here's this little echo here. Okay, and very often what we're trying to measure is delta T, the time between these two echoes. But if there's a little flaw in the material, like I've drawn here in dashed, we would expect to see a little echo in between the front and the back wall echoes. So the fact that we don't see any echoes in between the front and back wall echo indicates that there's no detectable cracks within this material, and it sort of gets a clean bill of health. The position of any echo we saw here would tell us how deep the crack was, and the amplitude would give us an idea of how big the crack was. So that's really the bread and butter of ultrasonic inspection, is flaw echo detection. We look for echoes from cracks or different sorts of flaws, and that tells us whether the material is good or not. And that, as I say, probably counts for half of all ultrasonic inspection. Another thing we can do is, if we're not looking for cracks, and if we know the material is uniform and has a constant velocity, speed of sound that we know, we can actually use this equation here. I should have mentioned here. This is what the E equals MC squared of ultrasonics, which is the velocity of sound is equal to twice the thickness of your sample divided by delta T, the time between the two received echoes. So the reason for the factor of 2 is that this back wall echo has to, you get the front wall echo that comes right away, let's say, and then the back wall echo, it has to travel into the material, travel to the back wall, and bounce off. So it actually does a round trip. It travels a distance 2x, not x. That's why you get this factor of 2x. Divided by delta T gives you the velocity sound. So this is how you calculate the velocity sound from delta T, knowing the thickness of the material. But if you knew that the material was uniform, and you could measure the thickness by measuring delta T. So imagine you had a big storage vessel of some sort, and you couldn't tell the thickness of the wall because the other side was in the earth. So you would kind of go over the tank with an ultrasonic transducer, looking for short delta T's, which would indicate small thicknesses, which might indicate corrosion, some weak spot in the vessel, and you might thereby put it out of commission if that weak spot was too bad. So these two methods, as I say, encompass non-destructive testing, looking for impurities or imperfections in materials. A more sophisticated type of ultrasonic inspection is what we call non-destructive evaluation, where we're evaluating a material. And often we do that by following the speed of sound, as you'll see in my example later. The speed of sound is sensitive, as we saw, to the density of a material and to its stiffness. So by looking for changes in the velocity of sound, we might well infer changes in material properties. We could map that out and follow the material all over different places, as we'll see later. A secondary sort of measurement we do is the attenuation. So here we see A1 and A2 are the amplitudes of these two, the front and the back wall echo. If we take that ratio of those two echoes, that gives us an attenuation. And if we follow that attenuation as a function of frequency, we can often infer things about the microstructure, the grain structure of the material. For the same reason that the sky is blue, different shapes, different size of particles in a material will reflect a sound at different frequencies differently, and so you might be able to get some indication by measuring the ultrasonic attenuation. Here's how we generate and receive ultrasound. So we excite our ultrasonic transducer with what we call an ultrasonic pulsar receiver, which excites the ultrasonic transducer with the 300 volts. And then it also, we're working in reflection here, okay? So we're actually sending our pulses of ultrasound towards the sample, receiving back our front back wall echoes that are identified here. The excitation we call the big bang, which actually saturates the output. So actually this blue wire here that goes to our CompuScope digitizer is actually a convenient signal that they've scaled to between, let's say, plus and minus a volt, rather than the 300 volts exciting the transducer. We've had one or two customers plug the probe connection into their CompuScope, and leads to a fairly speedy repair, I'm afraid. The ultrasonic pulsar receiver also furnishes a trigger out pulse. That is to say, a pulse that is simultaneous with the excitation of the transducer, the big bang we call it, and that can be used as a sort of a starter pistol. We externally trigger our CompuScope with that, so every time after the trigger point, it gives us how long the echo occurred after the excitation of the transducer. This is called an A scan. We've got the ABCs of ultrasonics. We'll show you the B and the C scan later. This is called an A for amplitude scan. So these are all the elements we need to create our ultrasonic scanning system. All we do is we mount our ultrasonic transducer on some sort of position control, and then we have a computer with our GaGe digitizer card acquiring the ultrasonic signals, and we move the ultrasonic transducer. We might move it continuously, do our measurements on the fly, or we might, ask it, please move 1 millimeter, take a waveform, please move a millimeter, take a waveform, and in this way we can scan in 1 or 2 or more dimensions and produce color maps of the part, which we'll show you shortly. So that was our introduction to ultrasonics. Now I'm going to move on to the ultrasonic example that I, as I say, participated in back in the 90s, and it concerns powder metallurgy, powder metal parts. You can make powder metal parts by squashing powder under a 100-ton press. Apparently, even back then, your car apparently has about 25 pounds of powder metal parts in it. And the classic powder metal part is the gear, because the gear is flat and it's complicated. It's got all those little teeth. Imagine having to machine all those little teeth with some sort of lathe or something. It's much easier to build a mold, a gear-shaped mold, fill it with high purity iron powder, which we've had since about 1980, and then we compact it under this huge 100-ton press, and out pops this gear out of the mold. But it's what we call green, just that's language from pottery, right? After you spin the pot, it's green, it's fragile, just like this this green part is. It's kind of like a, you know, a sand castle. Okay, it's a little more strong and resilient than that, but it really will fall apart quite easily. And that's because the grains that we've compacted, the powder particle grains are kind of held together in a jigsaw puzzle-like pattern that really isn't very strong. So in order to strengthen the part, we have to sinter it, which we put it in a furnace and we bring it up to something like 2/3 of the melting point of the material in Kelvin, okay? And we leave it for whatever, bake it for whatever time it is. And what happens is the grains, the powder particles, sorry about that, I'm trying to use my laser pointer. They fuse together, okay? So instead of having these separate grains, they fuse together and we end up with this porous material. It might end up with 5 or 10% porous, and it's not quite as strong as the pure zero porosity material, but it might be 90% of that. So you've more cheaply made a part that's almost as strong as pure steel at a much lower cost. So what did we do? We instrumented, we made ourselves a little punch rod, a pair of punch rods and a die for making these little powder metal hockey pucks, okay, that we compressed in our 100-ton press, sorry. We also had what's called an LVDT for measuring the position. So the upshot was we could measure the thickness, okay? We could measure the thickness of our hockey puck all throughout its compaction. And at the same time, we had this ultrasonic transducer that sent sound through one of the punch rods, using it as a buffer rod. Again, we get our front and back wall echo. We have the thickness. We can use our magical equation to calculate the velocity of sound. And here we are tracking the velocity sound all through the compaction. So as we loaded up the material, the grains sort of scrape by each other and the velocity of sound increases markedly as both the density and the stiffness of the material are increasing, more the stiffness, as I said. And then we sort of reach a sort of saturation region where the particles are held together by pressure. So that's why the sound travels nicely through it. But as soon as we let off the pressure, eventually the grains sort of separate and the velocity sound drops, because now we're going through these looser, more jigsaw puzzly type connected grains. So now, as I say, we've got the green part fragile but in the right shape. And so having monitored the ultrasonic properties of the powder as it was being compacted, we also had a furnace that was equipped with a novel way of generating and detecting ultrasound, which is called laser ultrasonics. So what we did was we had a very fast femtosecond type laser. Our furnace had quartz windows, so we could send this pulse of laser light through to hit our little cooking hockey puck. And when the pulse of laser light hits one side of the sample, it heats up a little volume element and sends a wave of sound propagating through the material. So here we're actually working in transmission, because the sound, when it hits the other side of the material, creates undulations on the surface, and we bounce another laser light off of those undulations and send it into an interferometer, a Michelson interferometer, which allows us to basically resolve those undulations, and we end up with an ultrasonic signal. I should have put it here, very much like we had from the piezoelectric transducer. So the upshot was we're able to monitor the velocity of sound during the sintering. I should have said piezoelectric transducers don't do well at high temperatures. The epoxy all melts off, and really, so you can't, it's not easy, or even in some cases impossible, to do high temperature ultrasonics with piezo. So our laser ultrasonics setup afford us that luxury of being able to follow ultrasonic properties at high temperature. So we identified a few different regimes during the sintering. We started out with this like sandcastle jigsaw puzzle like green part. As the temperature increased, the grains melted together, And then at late times, we had the pores kind of coarsening, turning from a square, in this case, to a more rounded square. And then when we lower down the temperature, we see very little change in the velocity of sound because the grains have been joined and they're joined for life. They're not going to fall apart anymore. And we only see a very small change in the velocity of sound. In order to more fully investigate this phenomena, we decided to create a sort of a two-level hockey puck. So as you can see here, we've got this, let me do this right here. We've got this die with a step in it, okay? We put the powder in here. And so by compacting this die, we end up with this two-level hockey puck arrangement. Now, if you think about it a bit, this is not the way to make two-level powder metal parts. Why? Because when you compact, you might imagine you might want to halve the volume, for example, during compaction. Well, to do that, you'd have to move this rod, let me get by half of this distance, but you'd have to move this one by half of this distance. So in order to keep the density uniform of the powder metal part, you would actually need two separate punch rods, okay, that were separately controlled. And this one would have to move faster than this one in order to maintain constant density. Well, we weren't trying to make good parts. We were trying to understand things. So we decided to use a fixed die in order to intentionally create density variance that we could see with our ultrasound. So you can, what I've shown here is a B scan. So this is a nice trick for allowing you to see multiple waveforms, sort of using color as a dimension. So what we've done here, here's our ultrasonic waveforms in blue, but you can imagine if you make the high voltages white and the low negative voltage is black and the zero voltage gray, you could turn this waveform into a one-dimensional color line, which is what you see down here. So this is near the beginning of the compaction. So this is the ultrasonic time in microseconds. Here's the pressure or load or time. We've really stacked multiple waveforms, but we're using color as the amplitude dimension. So here you can see the front well echo. It's always in the same place. That's this echo bouncing here. It's always in the same place, but it does diminish in amplitude, you can see over time, as the powder metal part densifies and more sound enters into it because it's getting better and better impedance matched. And then we also see these two echoes from the two back walls of the two different parts of the die. Here's the first one, here's the second one, and as expected, they come in for two reasons: because the part is getting thinner, so there's less distance to travel, but also the part is getting stiffer, so the sound travels faster. So it's a kind of a double whammy effect here. So this is a brightness scan, which is a standard display used by ultrasonic people, and it's the B in the ABCs of ultrasonics. Here, what we did was we centered our two-level hockey puck, and then we chopped this central L, okay, you can see here, out of the hockey puck, and we laid it down and put it in a conventional ultrasonic scanning system, and we measured the front and back wall echoes as always, delta T, and we measured the thickness with a micrometer, so we were able to work out at all positions in the sample the velocity of sound here, and we've created a sort of velocity map, which is called a C scan, C for color. So you see these are ubiquitous in the ultrasonic world, and you can see we've really got a really nice non-destructive inside view of what's going on inside this powder metal part. So as we might have predicted, the powder inside the short part of the die is uniform and high. That was subjected to a very high pressure, and so it's up in the steel velocity ranges of 5 kilometers per second and above. But then, not surprisingly, the longer, looser section of the die has gray or lower velocity, lower density velocity values, and then we get this kind of interesting low density line, which I've shown as a dotted here, you can kind of see how that might happen because, you know, the powder sort of squashes by the fixed powder in the small end. So you can see the great power of this ultrasonic scanning technique. We'd be able to measure the density all over the part, and you know, we could tune our powder metal process as a result of feedback from this sort of C-scan. So that's the practical example. It's given us an idea of what some conventional ultrasonic techniques and not so conventional techniques are. So let's examine some of the GaGe digitizer features that we can exploit in our ultrasonic inspection. First, we'll focus on the banner specifications, the most important of which is sampling rate. So generally, the higher the sampling rate, the better, but how much do you really need? And Mr. Nyquist tells us that you need, in order to reproduce the frequency of the signal, you need to sample at least twice the frequency of the signal. And we've done that in the lower curve there. And you can see it gives a pretty lousy view of the ultrasonic echo. Remember, we're trying to localize the position of this echo so that we can calculate things like delta T or determine the positions of echoes that correspond to flaws. If I go to the other end where we're sampling at 10 times the frequency of the transducer, we get a good view of the ultrasonic echo, and we're really able to localize its position. And then the 5x oversampling is sort of in between. If we just simply pick the biggest point as being where we'll call the position of the echo, well, then we're going to be limited to half, worst case, right, half the sampling interval. So we can see on the 5x here, you know, the real position of the echo is this dotted red line, and we can see we're right almost in the middle. So that means if we pick this point, we're going to be off by about half of a sampling interval in our determination of the echo position. Here we'll do better, not only because the sampling rate is smaller, but another thing we can do if we do a little more sophisticated technique is to interpolate. But I argue you still really need this 10x oversampling factor in order to get a good parabolic interpolation here. If you were trying to interpolate way down here, you wouldn't get a good interpolated point. So really the moral of the story is you really want to sample at 10 times the central frequency of your transducer. So that's sort of performance in the X direction, which is time in this case. Let's talk about performance in the Y direction. So what we need in ultrasonics really is high resolution, 14, 16 bits ideally, for the detection of small echoes. So using the impedance, the acoustic impedance values that we showed in the table previously, we can work out the biggest echo that we can expect from the back wall of a steel sheet in water. Okay, so this is a very common case. A lot of steel parts out there. We typically scan them in water, and all you're going to get is this wimpy little echo here from the back wall, okay, which works out to be about 1% or 2% of the size of the front wall echo. Now you can't amplify this. You can't lower your digitizer's input range, because if you do, you'll clip your signal. So you're forced by the amplitude of the front wall echo to keep your input range of your digitizer being no smaller than the amplitude of that first echo. So that limits, as I say, the fidelity that you're going to see on the reflected echo. In fact, if we digitize that signal with an 8-bit digitizer, which gives you 256 levels across the entire range, you can see that our little backwell echo only covers about 3 digitizer levels. Okay, so it's only got an amplitude of about 2, and that's giving you a really lousy representation of the echo. If I go to a 14-bit digitizer, that's 6 more bits. 2 to the 6 is 64. So that means for every level here, I actually have 64 separate levels, and that's allowed me, even with this noise that's on the signal, to get a much better representation of the echo. So this is probably the biggest advantage of our digitizers in that and transfer rate, is that with our high resolution, we're good for acquiring the high dynamic range signals produced by ultrasonic inspection, specifically seeing the very small echoes that could be arbitrarily small, because remember the flaw can be arbitrarily small. So with 16 bits, you improve your flaw detectability limit. So that's a very real advantage for ultrasonic engineers and technicians. An interesting trick we can pull in ultrasonics, because although the signal's high dynamic range, the high dynamic range parts are separated in time, okay? So here you can see high dynamic range means there's big amplitude and small amplitude parts, but they occur at different times. That doesn't have to be the case. We could imagine taking two different frequencies, a low amplitude, high frequency, and a low frequency, high amplitude, mixing them together. Well, then the signal would always have a big amplitude, even though it had big amplitude and small amplitude parts. But because of the temporal separation, we can pull this double range trick. So what we do is we split the signal in two with an RF splitter. We split our ultrasonic signal. We put it into the two channels of our digitizer, and we put them on two different input ranges, in this case, plus or minus 1 volt and plus or minus 0.1 volts, or plus or minus 100 millivolts. And this way we can look at the front wall echo on the bigger range, but then for the smaller echo, we can look at that on this small range. Now we get clipping of the first echo, but we get a much better view of the second echo, okay? This trick only works if the two channels of your digitizer are highly simultaneous, highly synchronized, which they always are on your GaGe card. And secondly, the amplifiers have to have good recovery time. You could imagine that after saturation, this waveform might have stayed stuck at the rail, as we call it, for a time, and it would have messed up the second echo. But that's clearly not the case. As soon as the signal comes out of saturation, it joins the big one here, to where, in fact, you could superimpose these, and it would join the upper signal right away. So the recovery time is very good. So this is the double range trick. Another important feature in ultrasonics is fast data transfer, because that leads to the benefit of fast scanning. If you can scan your part in, let's say, 30 minutes instead of an hour and a half, you can scan 3 times as many parts, and time is money and all that. So typically, you're scanning your part by going in a 2D pattern, in a grill-like pattern like this. Okay, so the ultrasonic transducer is moved in the water by a robotic arm back and forth like that to scan the entire sample. Of course, we're only using 6 lines here. In reality, you might scan it with 1,000 or 10,000 lines. As you're going along a line, you're triggering repetitively the ultrasonic signal, and each one of these triggers corresponds to a different position along the material, and so that's how you build up your image, by having multiple ultrasonic waveforms. Of course, the quicker you can get those waveforms, the quicker you can execute your scan. In the old days, before data streaming, we would do this by with our multiple record feature. So we've got this powerful multiple record feature that allows us to stack waveforms in the card's onboard memory. Our GaGe digitizer cards typically have gigasamples of onboard memory, which means they can hold millions of 1,000-point waveforms, which is typically what you use in ultrasonics. And here we show them here as being different, but being stacked in the card's onboard memory with rapid sub-microsecond rearm time in between each acquisition. So after acquiring one waveform, the digitizer only needs about a microsecond before it's ready for the next one. And as I say, you can stack thousands or millions of waveforms in the card's memory, but at some point you have to download it. And typically you would do that at the end of a line. Sometimes they don't even take data on the way back, but even so, it takes time to turn around. and you can exploit that time to download the data from the card's onboard memory to the PC's RAM, where you can store it and use it. We have a very fast data transfer speed at up to 5 gigabytes per second, so you can flush that memory pretty quickly. That, as I say, is the older approach. Nowadays, we have data streaming, which means that you can start the download of the data while the data are being acquired. So you may not have to wait so long to flush the memory before starting to scan the next line. And again, since we can stream at data rates of 5 gigabytes per second, we can do that. That's how most are doing these. Sorry, my car mechanic. That's how most are doing high-speed scanning these days. So that, just to reiterate, is a very important feature of our digitizer, the fast PCI Express data transfer speed. Ultrasonic people know that there's no way they would want to, acquire their waveforms using an oscilloscope and then offloading them through a slow cable connection, because the scan would take dozens of times longer as it would from a card. Now we're going to talk about synchronous triggering, or for starters, asynchronous triggering. When you have a signal, as most are, that are unrelated to our sampling clock, well then the card can trigger any time between two data points. So here I've shown a bunch of triggers that might occur on the card, and depending on whether the trigger occurs just after the last pre-trigger point or just before the trigger point, it'll be logged with the same trigger position. The upshot of this is that if you take repetitive waveforms, they dance back and forth, left and right. There's my curve, but dance back and forth, left and right by exactly one sample. We get people occasionally calling and complaining about this. This is no failing of the GaGe card, but one sample jitter is a fundamental consequence of an asynchronous signal and sampling clock. So what we have though on our GaGe card, one way to beat that jitter would be to provide an external clock to our card and a trigger that's also synchronous to that clock. But external clocking is always a headache if you don't have to do it. You have to, in order to do it, you have to have a separate signal generator and so forth. On our board, we provide actually what we call a trigger out signal. So when the card triggers, in this application, we trigger the card in software, and then it spits out a synchronous trigger out, which always occurs on the same phase of the sampling clock. In reality, it would occur a little bit after the trigger point, but it would always have the same phase relationship with the sampling clock. And if we trigger our ultrasonic pulsar receiver with this signal, then we can beat the one-point jitters we'll show you in this next slide. So here what we've done is not taken an ultrasonic pulsar receiver, but just a regular electrical pulsar that produces pulses that look like this here, okay? And in the first application, we're using the pulsar through this black wire to trigger the CompuScope digitizer. And when we do that, if we zoom in on this falling edge of the pulse, we can see indeed here we've taken repetitive waveforms, probably about 10. We can see they dance back and forth by exactly one sample, which is 2 nanoseconds in this case. But you can see if I draw a horizontal line, the bottom of this intersects the top of this. So that indicates that the width of this ribbon of multiple waveforms is equal to exactly one sample, as we expect. But if we reverse the arrow of triggering and make the GaGe card the trigger master, make it trigger the pulsar with our trigger out pulse, this pulsar's pulse kind of inherits the synchronicity of our trigger out pulse, with the upshot being that when we zoom in on multiple acquired pulses, again, this section, the falling edge, they line up perfectly. See, they fall so perfectly on top of each other, you almost can't tell that there's more than one. You can see there's a bit of divergence here. But you see, we've improved the jitter from being about one sample to being certainly better than a 10th of a sample, maybe better than a 20th of a sample, just by using this trigger out pulse. Okay, so this has real value in ultrasonics because, of course, you're trying to determine the positions of echoes, and if they're jittering back and forth, that's going to limit the accuracy with which you can determine that position. Other advantages to the trigger out are that you know, if your pulsar were doing the triggers, there's always the chance that you could miss a trigger because you weren't ready. Shouldn't be with our very fast rearm and everything, but in the trigger out case, you're generating the trigger, so you can never miss them because you're generating them. You won't generate them, so you can't miss them. Similarly, you don't have to wait around for triggers to occur. As soon as you're ready, you can output that next trigger out. So those are a couple of secondary advantages to trigger out. Next, I'm going to discuss what we call our expert Fpga firmware options. So the basic design of our card is an Fpga, which is a field programmable gate array. That's like a breadboard of configurable digital circuitry, but it also has sophisticated elements like processors inside it. So it's sort of the brains of the card is this Fpga. We don't use a CPU because we need to move data very quickly. So for that, we like to exploit the circuit-like architecture of the Fpga as opposed to the CPU. We connect the ADCs that sample the signal to the Fpga, who pass their data onto the onboard memory. Where's my cursor? Here's the ADC passing its data on to the onboard memory, which eventually gets downloaded to the PCI Express bus. Now, our Fpga is kind of half full or half empty, depending on your philosophy of life. And so over the last decade or so, we've taken to actually, rather than just delivering the raw data to the user with the greatest fidelity and as quickly and as easy to use as possible, we've taken to doing some onboard processing of the data. Okay, I sort of call it a pre-processing. You want to do some brute processing here. Separate the wheat from the chaff. Get rid of the garbage and keep only distill out, to mix some metaphors, only the good stuff before you send it on its possible bottleneck journey through the PCI bus. So this is what generally our expert firmwares are, but I'll talk about a couple specific ones that are uniquely appropriate for ultrasonics. The first, and I think most important, is our signal averaging firmware. Well, what's signal averaging? Well, signal averaging is where you have a repetitive signal, as we often do in ultrasonics, where the underlying signal is identical upon each repetition, but the noise changes. If we take these waveforms and we sum them up and then divide it by the number, which is the way you average, then we can average away the noise, which is uncorrelated with the trigger and the signal, while bringing out the signal, which is. So here we show if we only do one average, we get this noisy echo, which of course is going to be, you know, make it tough to determine the peak, thereby where the echo is situated. But if we take 100 averages, we get rid of a large amount of the noise, and so can determine the position of the echo a lot better. In fact, elementary statistics shows that the noise amplitude should drop as the root of the number of averages. So if you take 100 averages, the square root of 100 is 10. So that means this noise should be exactly 1/10 the amplitude of what it was initially. So if you keep going, you can eventually average away the noise completely. Now, of course, we've always been able to signal average by downloading waveforms. So, you know, acquire 1,000 waveforms, download 1,000 waveforms, sum them up in software, divide by 1,000, and you've got your signal average waveform. But what we're able to do with our onboard signal averaging, our expert signal averaging, is to do the summation in our Fpga. So now we'll still take 1,000 waveforms, but the Fpga will add up those 1,000 waveforms and will download only the averaged or sum waveform that results. So now we've cut the PCI traffic down by a factor of 1,000. We can increase our trigger rate correspondingly because we can average so quickly, and we've reduced that bottleneck, as you see. So by doing the averages on the board instead of in software, we both offload the job from the the PC, which let's face it has a lot of work to do already anyway. And secondly, we've reduced the PCI data traffic, so we can increase, always the game, right? Increase our trigger rate, so we can increase our scan rate and do our scans more quickly. So that's a great feature for ultrasonics. Our final feature I'll show here is our ultrasonic encoder firmware. I won't go too deep on this, but basically the stepper motors that typically move the sample in an ultrasonic scanning system are stepper motors. Every time you basically, they're driven by a square wave pulse like this red pulse here, and each time the stepper motor gets a pulse, it moves one step, which might be 1/10 of a millimeter or something. The advantage of our expert encoder firmware is that we can force the card to trigger after a fixed number of steps, okay? So that the card is automatically triggered, let's say every 10 steps, which in my example would be every millimeter. By doing that, you eliminate all kind of handshaking between the PC and the stepper motor. It no longer has to ask what the position is. It's automatically being triggered every 10 steps. And again, this allows us to increase our scan rate significantly. So if we combine our elements, our GaGe elements here, we've got the PCI bus that is very fast for getting the data into the PC. We've got our trigger out in order to make our ultrasonic echoes synchronous with our digitizer so we can get the best possible jitter. We may be signal averaging to improve, reduce the noise further on our signal and localize our ultrasonic echoes. And finally, we're having our ultrasonic transducer move using our stepper motor firmware, so nobody has to have this back and forth of, you know, where are you? Thanks, all this business. It's all done automatically for the very fastest and best ultrasonic scans money can buy. So here's a list of the features that the GaGe card has and the benefits they afford in ultrasonics. We've discussed that the GaGe cards have high sampling rate, up to 6 gigasamples per second, which affords 10 times oversampling for ultrasonic signals that we argue we require. We've got GaGe cards have generally high vertical resolution of 16 bits, which translates into the direct benefit of a very low echo detectability threshold. We've got our multiple record capability to stack waveforms in our onboard memory with sub-microsecond lightning fast rearm in between acquisitions, which gives the benefit of allowing the customer to use a fast trigger rate. We've got our fast data transfer speed and streaming, which allows us to get the data off the card quickly, again, to improve the overall scan rate. We've discussed our trigger out feature, which allows for sub-sample trigger jitter and localization of echoes. And then finally, our 2 expert onboard processing capabilities to signal average and reduce noise, and to be triggered by the position encoder for the fastest possible scan rate. For the final slide, I'm going to show you some ultrasonic applications that we've been involved in, some with industrial materials. So we work with a semiconductor company that uses ultrasound to assess silicon die adhesion to the package, okay? So you take your little silicon die and glue it down somehow to the chip package. And that contact, that adhesion has to be good so that silicon die is able to dump its heat to the package. If it's not in good contact with the package, it'll heat up and then maybe fail. So what they do is they bounce. Sound is excellent. Ultrasound is excellent for studying interfaces. If the silicon is well bonded to the package, if the die is well bonded, then the sound should go right through the interface and get very little or even no echo off of that interface. Conversely, if the silicon has not adhered well to the package and there's some sort of gap, it becomes an interface off of which we can reflect echoes, and basically the amplitude of the echo that you receive gives you an idea of the badness of the bond, and you can set some sort of criterion and eliminate badly bonded silicon dies. We've worked with companies in the rolled steel business, in this case using EMATs, electromagnetic acoustic transducers. These are also non-contact transducers like laser ultrasound. You've got to have your EMAT very close, I believe, within a millimeter of the rolled steel, and then it uses, with currents, it induces, and magnetic fields, it induces motion in the steel, creates ultrasound that you can use to measure the thickness of the rolled steel and determine if it's what you want it to be. If it were to drift or change, you could correct it. Another application we're in is pipelines, where they use surface waves to detect corrosion in the pipeline. So basically, use a surface wave, you send it around the diameter, around the circumference of the pipeline. You send it out, and it comes around and hits you in the back of the head. As I alluded to before, just like waves breaking on the beach, the speed of propagation in a thin pipeline depends on its thickness. So if you have a good pipeline, then you know when you should receive the surface wave, go all the way around the tube. But if there's a thin spot because of corrosion, that'll either slow down or speed up the wave, and you'll get your echo earlier or later than you expected it, and that will tell you that you've got some corrosion that you've got to look over. So these people make these crawlers that crawl sometimes even through the woods, judging the integrity of the pipeline. Finally, we worked with people who build CANDU reactors, nuclear reactors, that are where the nuclear charge, sorry about that, resides inside zirconium tubes that are used to cool the nuclear charge. And so these tubes can degrade, need to be inspected just like pipelines. So they do that in very much the same way. Another big application for us is medical ultrasonics. We've been in another number of different techniques. One is called intravascular ultrasound, Ibis. So you send a catheter into a patient's blood vessel, and then that catheter has on the end of it a sort of a searchlight, like a. Are you not hearing me?
We've got you now. We've got you, Andrew.
Okay, Carmen is phoning. Okay. So you've seen me the whole time. Was there a glitch there?
Yeah, no, you're fine.
Okay, good. Okay, so just to finish off, so as I say, ultrasonics, intravascular ultrasound bounces sound off of the plaque in the blood vessel, and they're actually able to measure plaque volumes and determine if intervention is necessary to avert cardiac events. We've also got a group doing a high intensity focused ultrasound, Haifu. So here you take a focused transducer that focuses the sound down into a point, and then at that point actually heats up and boils the tumor. So this way you can actually boil a tumor remotely rather than going in with a scalpel and cutting it out, which of course is a lot more invasive and damaging. Finally, we've got an application of ultrasonic levitation of pharmaceutical droplets. So it's very much like in a printer. Apparently, this is also used in printers where you levitate droplets of ink onto the paper, whereas here they levitate droplets of pharmaceutical liquid, move it around, dispense certain amounts, very precise amounts. So those are three pretty cool medical applications in which we're involved. So I don't know where I dropped out there, but I'm guessing I was pretty close to through this final slide.
Yep.
Okay, so what I was going to say is I hand it over to you, Susie, for questions, if any.
Okay. I don't see anything in the chat screen at this point. Did anyone have any questions or comments? You're welcome to unmute your phone and go ahead and ask any questions. Okay, well, I guess no one has any questions. Thank you so much, Andrew. We really appreciate it. And I will get everyone out a copy of the presentation as well as a link to the recording. So if there's anything you need, you can always contact me as well over at Vitrac. My email is susie.abbott@vitrac.com. Thanks again for your time this afternoon and have a great afternoon.
Okay, thanks a lot.